Okay, hello and welcome, and we're going to be having a look at trigonometry, trigon, trigonometry. I think that's about right, and triangles. Okay, well, I suppose trigonometry is all based on triangles, but we're going to have a look at the ratios of trigonometric identities. So, like if you had sine x. No, sorry, if you had sine 0, it's been worked out that sine 0 is 0, and if you had like sine half, that equals 30 degrees. Okay, and we're gonna investigate the sort of proof, not really, yeah, the sort of the proofs behind all these different ratios. So, um, you know, we have these angles. Okay, 45, 60, and 90. And from these angles, you have along here you have a sine, cos, and tan. Okay, and so what you have, right. So, for example, as I just said, sine 0 equals 0, but why does sine 0 equal 0? These are all just like identities that you use deeper into trigonometry that just make life a lot easier. I mean, the purpose of them is to make life a lot easier. If you see sine, if you've got a sine x in your calculation, okay, you come across sine 0.x. Basically, you know that you can, if that equals a half, then you can just forget the calculation between the sine and the 0.5 and just do the sum. Okay, so that's why these identities are very, very handy. So I'm going to try and show you how we fill in all these different squares. And the way it was done, okay, just so everyone knows, it had nothing to do with my mathematical skills. Just bring the mouse over here. Okay, so there are two triangles that we use to derive these ratios. One was an isosceles triangle, which I will remind you of the significant properties of which. Okay, so that's an isosceles triangle, and the properties that an isosceles triangle have is that two sides are of equal length, denoted by these lines here, and two angles are of equal size. Okay, so we know that's a right angle, and if these angles are the same or of equal size, then we can, and they're 180 degrees in a triangle, then we know that there's 45 degrees in the angle's 45 degrees, and so is this angle. But I'm not going to write that angle down because it's not just yet anyway. It's not necessary for what I want to show you. So what some very clever person did, or I think is clever. I mean, mathematicians that I've come across sort of see this as pretty easy to derive, but it's I would never think of it anyway. So I'm going to show you what happens. So these lengths. So we started off giving these lengths an actual number, okay, and it kind of doesn't matter what number you give this triangle, which we'll find out why, because what we're trying to gain from knowing this length here, these lengths here, is what the hypotenuse length is, and that's why it doesn't matter, because if I just pick 2 and a 2, then the hypotenuse will just work out as something else up here, but it will still be equivalent. Okay, so the easiest number to work with is 1. Okay, so let's just make the length of these sides 1. And now we can work out this length here, the hypotenuse, by using Pythagoras. And should know, but if you don't, that Pythagoras has worked out that a squared plus b squared equals c squared. Okay, and so in this instance, this will be 1 squared plus 1 squared equals the hypotenuse squared. Okay, let's just call it h for now. And so in working that out, well, we can, hold on a minute, that's quite significant. So let's just scroll down a little bit. So 1 squared plus 1 squared is 1 plus 1, which is 2. Okay, let's just write the h to that side. So we know we've got 2, and then we had a square there, so the opposite of a square is square root. So then you end up with your hypotenuse as a 2 squared. And we'll leave it in that form. We won't work that out. We won't plug that in the calculator and get, whatever 2 squared is. It will just be decimals. We want this clean, so we're just going to keep it in what's known as third form. Right, so what's next? So we've worked out, we've chosen arbitrarily 1 and 1, and we've worked out the hypotenuse. Now, let's work out the ratios, the sine ratios. Okay, so we should know that let's do the sine of 45. Okay, so let's start sine 45, and we know that the sine equals SOHCAHTOA from SOHCAHTOA, so it's SOH. So it's O opposite, so that'll be 1 over hypotenuse, which is 2 squared. 2 squared, sorry, 2 square root of 2. So, and that's what sine 45 equals. So if we want to fill in our little chart here, sine 45, we'll just write sine 45 here. However, the convention in maths, and this is one of the things about mathematics that is a little hard to grasp sometimes, and is the fact that they'll just have conventions, they'll have preferred ways of writing equations. So what the convention is to, they don't like to see this square root on the bottom, on the denominator. So basically they will do this. So if we had sine 45, I'm just doing this completely explicitly so you can see, and we basically want to get rid of the square root on the bottom. So in order to do that, we just square root the we times everything. So we times in that, and we times in that, and the square root of 2 times square root of 2 is 2. Okay, so that's how you get that, and then you're left with 1 times the square root of 2, which is just square root of 2. For those of you who don't understand why, because this was something I was like, why is the square root of 2 times the square root of 2? Seems quite weird, but imagine if you did the square root of 9, this is an easy example, times the square root of 9. And can I just quickly aside say, I've just written a multiplication here, whereas I've written a dot here. Now, this is what I'm talking about, exactly what I'm talking about in mathematical convention. A dot suffices in this instance rather than a cross. But now I've gone back to using a typical multiplication sign, just so I can, because this is more sort of appropriate, for less experienced mathematicians. So I just made it easier to use that. So that was just an example of where you can just flit from one convention to another sometimes, and then in other ways you can't. But anyway, back to this. So what's the square root of 9? Is 3, because 3 3s are 9. So square root of 9 is 3, and then times the square root of 9 is 3. So 3 times 3 is 9, and there you have the reason why the square root of, and that works for every square root. So that's what we've got. So we've got sine x equals the square root of 2 over 2, and let's just fill that in. So I haven't made these lines very neat. So it's a nice colour. Square root of 2 over 2, and that's supposed to, if you're not going to use a calculator, it means that if you come across sine of 45 and you know it's the square root of 2, then it should be an easy calculation to do. So how about let's carry on with this triangle, and let's do what should we do? Let's do cos. Let's do the cos angle. Okay, so what's cos 45? We're going to work. Should be enough space over here. So what's cos 45? Oh, stick with the colour. Right, and that is SOHCAHTOA. So that's the adjacent 1 over hypotenuse square root of 2, and that looks very similar to the sine of what we just had just now. So once again, we want to take that to the top. I'm using kind of the mathematical language I'm using. You wouldn't really say take that to the top, but it doesn't really matter at the moment. I'm just trying to show you how we did it, and I haven't explained this because we've just done exactly the same. So if you want to find out how I've done that, then just have a look at what we've just done there, and it's exactly the same thing. So cos 45 is also the square root of 2 over 2. Okay, and let's do the tan. Let's have the colour. Let's do the tan. So tan 45 tan 45 equals TOA. I mean, I'm not at the stage where I can really remember these just off by heart. That will happen, naturally over time. So opposite of tan 45 is well, 1 is the opposite, because the opposite is, if that's the angle dealing with, then the opposite is the opposite of the angle, and we want the adjacent, which is 1 over 1. That's the adjacent, and because adjacent to the angle. I mean, some people say that, well, that's also adjacent to the angle, so I hate that explanation when they say, well, because that's adjacent. I do it because I start with the opposite. I know that it's the opposite of the angle, and I know that I look at the triangle and I kind of see that that's the hypotenuse, because it's the longest line, and then it sort of makes sense that that's then the adjacent, because it is the adjacent of the angle, but it's kind of not as long as that. So tan 45 is tan equals 1. So let's fill that in. 1 divided by 1 is 1, I'm sure. You would have worked that out. Okay, well, I've changed colour. Shouldn't have done, really. Let me just get a colour similar to what we had, just to keep that. Right. Okay, so God, I can see that we've gone to 15 minutes. So that's how we've derived the sine, cos, and tan 45. And in the next video, I'm going to show you how we do the same for 30, for sine, cos, tan 30. See you in the next video.